I'm Mr. Bishop, the guy on the soapbox there. This is Chapter 3, Day 4. We're still talking about linear programming, and specifically today, we're going to talk about the fundamental theorem of linear programming. So some things that we've been successful doing so far leading up to today. We know how to graph and shade, right? Inequalities or systems of linear inequalities. Now we call those constraints from a real-world scenario. So we've been successful in doing that. And since we shade false, right, when we go to shade these things, we practice shading false. That means the feasible set, when we get done, our feasible set will be the open region, the open area. So that means I don't have to look at a bunch of weird shadings. If we shade false, I know that our feasible set is actually just the open region. And just to refresh you on what a feasible set is, it says, recall, our feasible set represents all the points that simultaneously satisfy every inequality of a system. So in other words, the region that successfully works for all of our constraints. So we've talked about what a feasible set is, and notice it says all the points that work, right? All the points that successfully work for our system. So the question is, which one of these points is actually going to maximize or minimize our objective function? Right? Which one's going to give us the maximum profit? Which one's going to give us the minimum cost? Do we have to actually test all the points? It seems like there could be an infinite number of points in any shaded region. So once you guys graph and shade, and you have this little area of or your feasible set, which one of the points is actually going to give us our maximum profit or our minimum cost? So that's where the fundamental theorem of linear programming comes in. This is what that theorem says. The fundamental theorem of linear programming says the maximum or the minimum value of the objective function is achieved at one of the vertices. That's a key word here. At one of the vertices of the feasible set. So the max or the minimum value of our objective function is achieved at one of the vertices, which means to find our maximum profit or our minimum cost, we just have to check all the corner points, or the vertices, if you will, right? Each corner point is a vertex. We just have to check each corner point in the objective function. We plug it in, and we find out which one actually gives us our max or min. So you notice there's my light bulb moment there. So for a brief little visualization of that, let's say we throw together a little feasible set. Looks like this. So let's say that little open area there is our feasible set. We did all the graphing, all the shading. We just have this weird little shape, right? And we want to know which point is going to give us the maximum profit. All we have to do is check the corner points. At one of those points, you will find the maximum profit in your objective function. So we just have to check the corner points. So in this case, that means 1, 2, 3, 4. We only have to check 5 points to figure out what the maximum profit for our scenario will be. Okay, so let's take a look at the worksheet for today then. I'm going to focus on a few of these problems with you and then leave the remainder for you to finish. So the first part here, it says a graph of a region labeled Fs for feasible set in the interior of the four-sided shape with these vertices is shown below right there. So here's our little feasible set. It says find the values of x and y that maximize the given objective function for the feasible set. So there's our feasible set. You know you've got these cute little corner points. Let's take a look at number 5. The objective function is x plus 2y. So which one of these points maximizes this objective function? So we need to start by plugging these points in. Right away, I think one that's not going to be the maximum is 0, 0, right? If you plug a 0 in for x and a 0 in for y, well, you just get 0. So we need to plug in each one to figure out which one gives us our maximum. So let's take 0, 5, for example. Plug in a 0 for x and a 5 for y, and we get 10 is our value from the objective function. So that may actually be the winner. Let's try another point here. How about 3, 3? If you plug in 3 for x and a 3 for y, you get 3 plus 6, which is 9, so that is not a winner. And then how about 4, 0? If you plug in a 4 for x and a 0 for y, well, we just get 4, so that's not a winner. So our winner is the point 0, 5 in this case. So 0, 5 gives a max value, right? Gives a max value of 10. There we go. So that's our objective here to start out with. We have a function, an objective function. Take a look at number 6, x plus y. We want to know which point on this graph will maximize that function. So I'm going to erase this. X plus y. Well, that one's actually really simple. You could probably figure all those out in your head. Again, I don't think 0, 0 is the winner. Right? If you plug 0 and 0 in, you'll just get 0 as your answer. 0, 5, you're going to get 5. 4, 0, plug it in, you get 4. But 3, 3 in this case, if you plug in a 3 for the x and a 3 for the y, you get 6. That looks like the winner. And again, all we have to do is plug in the corner points to check and see which one gives us our maximum. So for number 6, the winner is 3, 3, which gives us a max value of 6. There we go. So 7 and 9, I'll leave you to do. Figure out which point gives a maximum value there. And then for these exercises, 9, 10, 11, 12, notice it wants to minimize the function. So you take your feasible set here. You've got 1, 2, 3, 4 corner points, and it wants to know which ones will minimize the objective function. So these 4 down here are minimize questions. Okay, and then I want to focus on 2 other problems here, starting with number 25. Number 25, it says we'd like to minimize the objective function 3x plus 4y subject to the constraints below. So these are the constraints. Okay, and the directions above say we need to optimize this scenario, meaning find the minimum or the maximum. We're going to graph, shade, look at the corner points, and figure out where our minimum or maximum is at. So for starters here, let's take the first constraint there and get y by itself. So subtract 2x on both sides and we get y is greater than or equal to negative 2x plus 10. And then keeping with my color coding scheme, the second constraint there in red, let's subtract x on both sides, and we get 2y is greater than or equal to negative x plus 14. We need y by itself though, so don't forget we're going to divide everything through by 2 here, which gives us y is greater than or equal to negative 1/2 x plus 7. So I'm going to go ahead and graph these first two lines. Negative 2x plus 10. Let's see, let's put a dot at 10. There we go. And then we're going to go down 2 over 1 for the slope. So down 2 over 1 each time. And let's go ahead and make our line. There we go. And for the red line here, we got a y-intercept of 7. So let's put a dot at 7 on the y-axis and go down 1 over 2. Perfect, they intersect right there. Down 1 over 2. And let's go ahead and make our line. There we go. Let's mark this up. And remember, we're shading false. So let's go ahead and indicate that here. We're going to shade false. Shade false. So for both of these lines, since they're greater than or equal to, we typically shade above the roof of the house, but now we will shade below the roof of the houses here. Alright, so for the blue line, let's shade below. And for the red line, let's shade below. There we go. And we can't forget about our last two constraints here. I'll do those in gold, right? X greater than 0, y greater than or equal to 0. So I'll put a horizontal line here for y equals 0. And then I'm going to shade below it because we're shading false. And then a vertical line here for x equals 0. And I'll shade to the left because we're shading false. Okay, so we're done graphing and shading. The feasible set is this big open area here. This is our feasible set. So it is unbounded, right? It sort of goes on and on. And just to kind of illustrate this here, I'm going to use my little pink highlighter tool to mark off the lines for the feasible set here. Okay, so even though this thing is wide open and unbounded, right? It keeps going technically all the way that way, and it keeps going all the way up. It still has corner points. That's really important. We need to identify where exactly those corner points are at. So let's start with identifying those corner points, and then from there we'll plug each one into our objective function, which is 3x plus 4y. Okay, I'm going to use a purple color for this. So where do these lines actually intersect? We've got one right here. This looks like 0, 10. That's one corner point, so I'm going to add that. There's a corner point. We've got one right there. We've got an intersection. I think that is 2, 6. So I'm going to add that to our list. And we've got one more corner point right here, which I think is at 14, 0. So we've got 3 corner points that we can identify. This is not a corner point down here in the corner, right? Technically, this line extends out forever. And same thing up here. This is not a corner point because technically that line would extend out forever. So where are the lines actually intersecting? Boom, boom, boom. So we've got 0, 10, 2, 6, and 14, 0 for our corner points. Okay, we need to plug each one into our objective function to see which one gives us a minimum value. Our goal is to get the minimum value here to minimize the objective function. So if we plug in 0, 10, 3x plus 4y, I leave it blank to start out. 0 for x, 10 for y. Let's see. 0 plus 40, that's 40. Okay, not bad. How about the next point there? 3x plus 4y. Leave it blank to start out with. We got 2 for x and a 6 for y. Let's see. That's 6 plus 24. That's 30. So 30 is the winner so far in terms of being the minimum value. It's the smallest number we've got so far. Last but not least, 3x plus 4y. That's our objective function. Plug in 14 for x here, 0 for y. 3 times 14, that's 42 plus 0, 42 for the overall value. So our answer is staring us in the face here. Our minimum value is 30, which occurs at 2, 6. So let's go ahead and give that as our final answer. The minimum value that we got through our objective function, we got a minimum value of 30 that occurred at the point 2, 6. There we go. There's our final answer. All right, so that's the gist. Let's take a look at one more problem here. Let's go to number 26 and talk about this one together. This one is a maximize problem. It says we'd like to maximize this objective function subject to these constraints. So again, we're going to graph, shade, and then look at which corner points will maximize this objective function. So to start out here, let's get y by itself in this first constraint. So subtract 3x on both sides, and we get 2y is less than or equal to negative 3x plus 36. I'm going to move this up just a hair here. There we go. Divide everything through by 2, so we can get y by itself. And we get y is less than or equal to negative 3 halves x plus 18. All right, so that one is ready to go. Let's get a different color here and look at the other constraint in red. Let's see, subtract x on both sides, and we get 4y is less than or equal to negative x plus 32. Divide everything through there by 4 to get y by itself, and we are left with y is less than or equal to negative 1/4 x plus 8. Alright, now that one is ready to go as well. Alright, so let's at least go ahead and graph the line parts of these really quickly. We do have a big enough graph here. It goes all the way up to 20 on each axis. So for the blue one, let's put a dot at 18 for the y-intercept. And then let's go down 3 over 2 for each dot after that. And I think it's really nice and important that you can map out these dots using the slope, because that might help us see exactly where these two lines intersect, if they intersect exactly on a coordinate point. So there's my blue line. There we go, and I'll shade it in a little bit. The red line has a y-intercept at 8, so I'm going to put a red dot at 8. Let's go down 1 over 4 for each dot after. See, and now we can see exactly where they intersect right there. All right, there we go. Down 1 over 4 and make my line. And as a reminder, remember we are shading false here. So since both of these are less than or equal to, we typically shade below the roof of the house. But we're shading false, so for both of them I'm going to shade above. So for the blue line, I'm going to shade above that one in blue. And for the red line, I'm going to shade above that one in red. And then I can't forget about our last two constraints here. I'm going to do those in gold again. So I'm going to put a line at y equals 0 horizontally here, and then shade everything below it since we're shading false. And then a line here at x equals 0, and shade everything below, or I should say to the left of that one, since we're shading false. Alright, so there it is. Our graphing and shading is complete, and since we shaded false, our feasible set, our feasible region is this open area right here, which is fantastic. I'm going to go ahead and highlight it in pink there so you can see it. It's kind of a weird looking quadrilateral. Alright, so with the graphing and shading done, we want to know which point in here gives us our maximum value for our objective function. And the fundamental theorem tells us we only need to check the corner points. So let's start with identifying the corner points. And then once we do that, we'll plug them into our objective function and see which one gives us a maximum value. So I'm going to use purple for corner points again. Right away, 0, 0 is in there. That's a corner point. I doubt that gives us a maximum value. On the x-axis here, it looks like we've got 12, 0 as a corner point. Up here at this intersection, this corner point, looks like we've got 8, 6. And then our fourth and final one up here looks like it's 0, 8. I'm going to put a purple dot there. Okay, so we've got our 4 corner points identified on this weird looking quadrilateral. Which one gives us a max value? Let's go ahead and plug these in. 7x plus 4y. The first xy point is 0, 0, so that one's not going to be a max value. That's 0. How about the next point there? 7x plus 4y. We plug in a 12 for x, a 0 for y. That's just 7 times 12, which is 84. All right, third corner point, we got 8, 6. So if I plug it into 7x plus 4y, we got an 8 for x and a 6 for y. So that's 56 plus 24, which gives us a grand total of 80. Last but not least, we've got 0, 8. So 7x plus 4y. Plug in 0 for x, 8 for y. That gives us 32. That's not a winner. It looks like our clear winner is going to be 84, which occurs at 12, 0. So our final answer for our maximization problem here, we have a max value of 84 at the point 12, 0. That's 12 for x, 0 for y. All right, and just to review, we talked about the fundamental theorem of linear programming today, which means once you identify your feasible set, the only points you need to check are the corner points. You plug those into the objective function and figure out which one gives you your minimum or maximum, whatever the problem desires. Okay, that's all for this video. Thanks for watching.